Hi, I thought it would be a good idea in this YouTube series to include just a demonstration of what the post-prediction process looks like end to end. So that's going to be what's happening in this video, just going through this pipeline file using the Python debugger, and we can look at the data throughout the process just to get an idea of how it actually works. So what we're doing here is we're making our list of models that we're going to be using. The list is only one model set long. And it's going to be made of the UNet class image segmentation for our class model, and our vector model is going to be using the newer version of SteveNet using the alt labels. For our eval models function, we're not evaluating the model really here, even though it is going to be spitting out accuracy metrics. But so our model set is just that one model that I described just now. We're going to be doing 3 trials. I'm just going to walk through on one, and then we can do the other 2. Show image choice to true means that we're going to be seeing the output image. Show true means that the true bounding box is also going to be drawn on that image along with our prediction. We're not going to be saving the image, we're not going to be saving the accuracy, and all valid was for doing the entire validation set, which we're not doing. That's what all those variables mean. So, going into eval models, now we're up here for model set and model sets. Our model set.name is a dictionary. And it is too long. We have our class model. Right, so this is when we're accessing kind of all these variables here at the very bottom. We're loading this dictionary, which has a bunch of specifications for the model structure. So, you know, SteveNet new and the correct generator, the loss, and I think like what outputs it uses, class or coordinate outputs, or both, stuff like that that we're going to be using later. So class model, and then we're loading the model weights using another function that uses some of those variables that we just loaded. So this one's going to take a while. And then we're doing the same thing for the vector model, basically. So our vector model, we're going to load that. We're going to track whether it's using the alternate labels or not. Load our vec model. And then we actually make our model wrapper, which is I think I mentioned it in another video, but basically you can use 2 modes. You can use this kind of a separate vector model and class model, or you can use one that just has a single model that has a class and vector output. So that's what's happening here. If we step into this function, type models is dict. We have 2 models, self-class model equals the class model, vec model equals the vec model, and it's not a combined model, which is the other version that we have. And it is using alt labels. Yeah. So now we return, and we have our model name. Okay, so now we're getting into the prediction here. So we are evaluating our model with our UNet classes as the class model and the new chords alt as the vec model. This true list and pred list is going to hold our true values and our predicted values. If all valid, we're not doing that. And for trials, we have that 3 trials passed down. If all valid, nope. Okay. So here is where we're loading our image to be used. We have this get data split image in our data file. So our get data split image, we're passing this get valid boolean, meaning that we're going to be using validation data. So stepping in here, we're going to be loading. So our valid data here is just a large list of all of the file names for our validation data. And we need a base path to know where to load them from. Base path is just a file folder, or a folder string, whatever you want to call that. So get valid. Now we have our choice. Our choice is just one of those random choices in there. So we have our JPEG file name, our mask PNG file name, which we're not going to be using, and our labels file name, which we are going to be using. So with open base path, now we have our labels, and they're floats in the format of a list of strings. We're going to be converting that later, and we're also going to be getting our image. So return image labels. Okay, so now we're back in that first function, our eval models function, and we have, where do we go? image labels. So one thing that we can do here, so this is what our input image looks like. I actually have a function that we can show image. So this is the function that we're looking at, an RGB image. It looks a little blurry here, so I'm not sure if plot loads that completely correctly. But we can see here. So you can also see down here the coordinates, the XY coordinates, and the RGB values of this vector. I don't know, kind of cool. All right, so our next thing is our model wrapper is going to generate predictions for each of those. We can step inside here. This function isn't too long. It is not combined. So yeah, we're just doing our vec model is going to predict the input, which is the RGB image, and same thing for our class model. So that takes a while. And cool. Okay, hold on one sec. So now we have our class spread. Does that exist yet? Okay, so something cool that we can do here is we can actually see what our class spread looks like compared to that image before. So you can see that the class prediction actually has this, you can see pretty clearly that it's defined the cat and has a pretty good idea of where the cat is. So this one should turn out okay. So going into this predict pose function, our predict pose, what are we passing here? That's important. We're passing our coordinates predictions, we're passing our class predictions, we're passing whether or not we're using alt labels, and we're passing whether or not we're going to be pruning our hypotheses, which we are. So this function is up here. If show class spread, so I have a bunch of testing stuff in here that we're not going to be using. Here we're finding, so we're examining that class's image that I just showed, and we're seeing if any of the pixels are over the threshold. So just to show that again, our mask threshold is one of these hyperparameters that I have up here. Where is that? So 0.9, so any pixel over 0.9, so all of these cat ones, once again we can see down here the values of each pixel, they're all around 0.99. And then there's some other spots here which might get included, but I don't think that they will. So population. So here our population is just a list of, I forget which order these coordinates are in. Apparently, according to my notation here, they're in YX format, which should correspond. Let's take a look at that image again. Show image. One thing that we can see here is that these pixels are all very close together. We can see, like, it goes 203 to 353, 354, 355, and that does seem to correspond with what we have here. There's, down at 203, so towards the very end. So this is like looking at the cat's foot, basically. But they all seem to be within the bounds of approximately where this is. Our x's go from about 300 to 400. And the x's do seem to be located there, and the y's go from about 150 to 200, which also looks to be the case. So we have another one of these test things here, which we can just ignore. And now we get on to our RANSAC voting. So I'm just going to do one iteration of the RANSAC voting. The RANSAC voting function is where? Right here. So the first thing in our RANSAC voting, what did we pass here? We passed our population of YX coordinates, and then we also passed our coordinates vector. So this is our coordinates predictions vector. So what this hypedict value is here, for each key point, the key points are denoted by these keys 0 through 8. We're going to be passing back a list of weighted hypotheses that this process is going to generate. So we have n in the range of number hypotheses. Right now it's at 50. We pop 2 random points. So we're just popping a randomly selected point from the population. And so we repeat that process twice. We have this P1 and V1. And so this V1 is from our coords prediction. we have our y and our x value from that point that we chose randomly, and these are our predicted values that we're going to be checking against our hypothetical key point here. So going forward, right here, so for I in range 9, so this is for our 9 key points. We're going to be doing the same process for each of them. We're going to be finding the slopes. We're going to be finding the y-intercepts, and then we finally find the line intersection. So our proposed intersection is right here at this y and x point for this. I think this is the centroid key point. We initialize the weight here at 0, and then for every voter that remains in the population, so the population minus these 2 points, we're going to be finding the y difference, we're going to be finding the x difference, we're going to be finding the magnitude of the difference to help us get the unit vector, and then we're going to get the predicted vector from our voter here. So our voter, we're looking at voter is this key point here, so that's also in YX format. In any case, we're accessing our prediction array, and then we're accessing just a subset of those predictions. So cool. If we were to take this here, we get all of the predictions for that pixel, but we're only interested in 2 of them right now. The first 2, since I is at 0, we're going to be going from 0 and taking a slice up and just take those 2. So this is what our vector looks like. We pass this into our RANSAC val, so we're passing this is our predicted unit vector, and then this is the actual unit vector, the difference between our proposed key point and the point that we're examining right now. So we pass that to our RANSAC val function. RANSAC val is, I think, just 1 line, or no, 2 lines. Here we're normalizing the second vector that we passed, the prediction. The predictions are trained on unit vectors, but they don't always produce unit vectors. This is a way to ensure that this value is actually a unit vector. And if you take the dot product of unit vectors, you get the cos of the difference in the theta between them. So we're checking if that is above a certain threshold, and if it's above a certain threshold, then we kind of give it a vote, or we increment the weight. So in this case, let's go here. We have our y1 and our x1, and then what is v2? So these are a little far apart from each other. I'm not sure if this one's going to get a vote. Nope. Okay, it's definitely going to get a vote. I didn't think that they were that close. So this is our generated value. They correlate very strongly, 999. That's the value that we're returning. So this value gets returned to above this RANSAC threshold, so this can be set wherever you want. I have it at 0.99, which is I thought would be a very high threshold, but every time that I've stepped through this manually, it has agreed. So that's pretty cool. So we do increment our weight, and that's the entire iteration. So we do that for what is happening here? For I in range 9. So for the entire population, after we do it for the entire population, we have the final weight that we can associate with this x and y value, and then we repeat that process for each of the key points. After that is all done, we can append our P1 and our P2 back to the population, so our population doesn't diminish as this process goes on, which could be an issue if you had a very high number of hypotheses. And so we can get out of this function right now and get back to our post-prediction function. And we're right here. For some reason, this line takes a really long time to complete.
So bear with me, I'll probably fast forward this if I can. Or cut it or something. I'm not going to watch this the entire time. I think it took about a minute last time. Which is weird because I went up out of this function. I guess it completes the entire RANSAC voting process. Not when I hit up, but after it completes the RANSAC voting process, I hit this 10. It's kind of a mystery how PDB works sometimes.
Okay, so we're back. If pruning, we are pruning. here, the pruning variable should be true. We're going to be using the standard deviation pruning. I can also do an iteration of this quickly. So let's take a look at what that looks like before we step in. So our standard deviation pruning, this is a way to prune hypotheses that we don't think, or that fall outside a certain range, which is basically what we're doing here. So for key, hypes, and hype dict, so we can take a look at our hypothesis dictionary right now. Well, actually that's kind of unreadable, so forget that. So we're looking at one key point right now, and then we have our hypotheses for that key point. So we get these either, I guess it's still yx coordinates, and then the associated weights for them. And we're just, we have these three lines here. So we're getting the y values and the x values. We're finding the mean using the statistics module for the y values and the x values. We're finding the standard deviation for the y values and the x values. And then we have this line here. So the hype dict key, so the key that we're using, is getting assigned to a new list where we're determining outliers. So if we determine an outlier, the outlier is not included in the list. This outlier function is just passing each element of this list. So in hypes, we already looked at hypes. We have our mean and our deviation. We have our x mean and x deviation. That's passed into here. So we're checking our y value against our y mean, and we're seeing if that's greater than our standard deviation for the y values multiplied by this scalar here, which I have at 2. And then the same thing for the x values. So if either of these expressions evaluates to true, then I believe that the element that we're looking at is not included. So we can get out of this function now. We did prune hype devs standard, and now we're looking at so now we have our prune dictionary. Let me find exactly where we are. So the mean, finding the mean isn't anything too special. It's a pretty simple process of taking a weighted average. I think we can just skip over that. When you go through the list and you're incrementing each of the x and y kind of cumulative values according to their weight, and then dividing those by the weight for each key point. So now we have our mean dict, which is a lot more readable than before. We have our average values for each key point. So if alt labels, that should be true, because we are using alt labels for our vector. And if alt labels is true, so why that's important is we're loading a different 3D points depending on whether we're using alt labels or not. So if we are using alt labels, we're using this alt points. We're loading this alt point file for our 3D points. If we're not using the alt points, then we're loading this bounding box file for our 3D points. So PTS3D, that's our array for our alt labels, where they line the 3D model. And then preds, we're converting this dictionary to an array to match this format. This is another testing line that we can ignore. So now and these are our draw points. So in both cases, this is the actual, this is the overlay that we're going to draw on our image, and we're going to be drawing our bounding box on the image. So in both cases, we just load the same file that we would have loaded if we were using the bounding box. Okay, so now our PNP function comes in. This is where we start using CB2. Let's just find that function before I step in. There we go. And we're passing in, so we're passing in our 3D points. These are our alt label coordinates on the 3D object model. We're passing in our 2D points, which are the 2D points generated by our RANSAC process. And we have our draw points, which is the bounding box that we're going to be drawing on the image. Also, we have as our default, I think that this is a distortion matrix or something for the Kinect camera that was used. So going through here, just a couple things to transform some of this data. And then now we're in our solve PNP method. So we're just passing the 3D points and the 2D points and the matrix, and we're letting this CB2 solve PNP function take care of that for us. So we can step through here. And what does that give us? This gives us our rotation vector and our translation vector. So T-vec, this is the apparently the distance of the camera from the cat in the object coordinate system, and the rotation vector, which is the rotation of the camera relative to the cat's coordinate system. Okay, so this is the points that we're going to be plotting on the object. The reason that we passed this bounding box, this is kind of like the inverse operation. Now that we have our rotation vector and our translation vector, we're interested in finding where a certain set of 3D points are on the 2D image. So we're passing through those 3D points and all of the camera information in the matrix again. And we use that to get this plot points, which is the image that we're going to be drawing, or the pixel locations for our bounding box that we're going to be drawing on the image. So we're returning that. We're finally back in this eval models function. Where exactly are we in the eval models function? A little lower than that. Y true, Y pred. Here we go. Okay. So if not res, that's just if if it fails to find population, which isn't really a problem anymore. We can ignore that. Okay, so now we have our Y predictions. This is our predicted values for the bounding box key points. We're going to be loading the actual true values from here. So we loaded the labels when we initially loaded this image. And we're just converting those to a list of floats, I believe. So Y true, and then these lists are used to generate metrics at the end of this. But we can see now, so we have our Y true and our Y pred values. There's Y pred, and here's our true labels. So these should correspond. 322 to 323 is a little off, 167 to 169, but you can see that they do correspond. They're definitely, there's definitely some accuracy, but a small amount of error. Where are we now? So here's where we see our metrics. For prediction 1 of 3, we have an absolute error of 2.3. So this is going to be a pretty good prediction. If show image choice, so we're going to be seeing the image here. This is us coloring. Right, so this is us loading the image initially. And the image is in RGB, but CV2 uses BGR, so you need to load it with that argument. Draw pose. So this is we're going to be drawing our predicted values on it. I don't think there's any point going through that function. You're just it's using CV2 to draw lines between certain points there. And then we also have this show true. I did choose to show true, so we're also going to be drawing the bounding box on there. And this is the different color. I think that our predicted value is in blue, and the true value is in green. So here is our prediction. As you can see, it's a pretty good one. Yeah, not a lot of error there. This image is still a little blurry. But yeah, so I'm going to let this process run 2 more times, and we can see how it does for the rest of them.